Hello students, welcome to grade 12 chemistry revision lesson on factors affecting equilibrium positions. At the end of this lesson, you will be able to list factors that affect chemical equilibrium, state Le Chatelier's principle, and define optimum conditions. Students, if you are ready, then we will get started. Factors affecting equilibrium constants. As we said, for reactions of the type AM, A plus BB to form C plus DD, the equilibrium constant Kc, equal concentration of C to the power of C times concentration of D raised to D divided by concentration of A to the power of A times concentration of B raised to B. Equilibrium constant is the ratio of concentration of the product to that of concentration of reactant raised to their respective coefficients. Now, what factors affect the equilibrium constant Kc? The equilibrium constant depends upon the following factors. 1. Temperature at which the experiment is performed. Therefore, equilibrium constant Kc of the reaction depends on the temperature at which the experiment takes place. Take this as an example. Production of ammonia by the Haber process. This reaction is exothermic. Delta H for this reaction, delta H is minus 92.2 kilojoule. You see? Production of ammonia from its elements nitrogen and hydrogen by the Haber process. Look, temperature in Kelvin at 298 Kelvin. K is 6.8 times 10 to the power of 5. At 400 Kp is 41. At 500 Kelvin, Kp is 3.6 times 10 to the power of minus 2. Therefore, a reaction at equilibrium has only one equilibrium constant at a given temperature. Equilibrium constants Kc depend on temperature. The same is true for this reaction, sulfur dioxide plus O2 gas to form sulfur trioxide gas. At this temperature, 298 Kelvin, Kp is 4 times 10 raised to 24. At 500, Kp is 2.5 times 10 to the power of 10. Therefore, equilibrium constants Kp or Kc depend on temperature at which the reaction takes place. This N2O4 gas is in equilibrium with nitrogen dioxide gas. Again, at 298 Kelvin, the equilibrium constant Kp is 0.98. At 447.9, at 500 Kelvin, Kp for this reaction is 1700. Therefore, Kp or Kc depend on temperature. 2. The form of equation which describe the equilibrium also affects the equilibrium constant. For example, the equilibrium constant of a reaction in the reverse direction is the reciprocal of the equilibrium constant of the forward reaction. If a given reaction at equilibrium is reversed, then the new equilibrium constant K prime C equal 1 over original Kc. Take this reaction, equilibrium reaction, hydrogen gas plus I2 gas in equilibrium is hydrogen iodide gas. For this reaction, the equilibrium constant Kc is X. When this reaction is reversed, it becomes 2 hydrogen iodide gas in equilibrium with H2 gas plus I2 gas. Now, the new equilibrium constant K prime C is 1 over original Kc. Therefore, if a given reaction at equilibrium is reversed, then the new equilibrium constant K prime C is 1 over original Kc. Hydrogen gas plus I2 gas in equilibrium with hydrogen iodide gas. Kc for this reaction is 54. Now revert this reaction. When the reaction is reversed, it becomes this: 2 hydrogen iodide gas in equilibrium with hydrogen gas plus I2 gas. The new case K prime C equal 1 over original case, which is 54. 1 over 54 is 0.018. From this, we can observe that the form of equation which describe the equilibrium affect the equilibrium constant Kc. The equilibrium constant of a reaction that has been multiplied by a number is the equilibrium constant raised to a power that is equals to the number. If a given equilibrium reaction is multiplied by n, then the new equilibrium constant K prime C equal original equilibrium constant raised to the power n. You see? Take this as an example. Hydrogen gas plus I2 gas, 2Hi gas. Original case, initial casing is 54. Now this reaction is multiplied by 2. The new Kc, which is K prime C, equal original Kc to the power 2. K prime C equal original Kc to the power n equal the original Kc is 54. 54 raised to the reaction is multiplied by 2 equal 2916. Therefore, if a given equilibrium reaction is multiplied by n, the new equilibrium constant, which is K prime C, equal original Kc to the power n. 3. The equilibrium constant for a net reaction made up of 2 or more steps is the product of the equilibrium constant for the individual steps. Look at this example. NOBr in equilibrium with NO plus Br2. K1 is 0.014. Br2 plus Cl2 in equilibrium with BrCl. K2 is 7.22. Now, these two reactions add up to give this overall reaction. If you add these two reactions, we get this overall reaction. Now, the overall K, which is K3, equal K1 times K2. Yes, Br2 will be cancelled by Br2. 2NOBr plus Cl2 in equilibrium with 2NO plus 2BrCl. The overall case equal K1 times K2 equal K1 is 0.014 times K2 is 7.2, which is 0.10. Consider the following reaction at 1200 Kelvin. CO gas plus 3H2 gas in equilibrium with CH4 gas plus water gas. K prime C is 3.92. CH4 gas plus hydrogen sulfide gas in equilibrium with carbon disulfide gas plus hydrogen gas. K double prime C is 3.3 times 10 to the power of 4. Use the above reaction to determine the equilibrium constant Kc for the following reaction at 1200 Kelvin. Now this is overall reaction. These two reactions add up to give this overall reaction. Now what is the overall K for this reaction? Overall K. K overall K overall equal K prime C, K prime C times K double prime C, because these two reactions add up to give this overall reaction. You see, CH4 gas, this will be cancelled by this. Carbon monoxide gas plus hydrogen sulfide in equilibrium with water gas plus carbon disulfide gas plus 4H2 minus 3H2 gas is H2 gas. Now K overall is K prime C times K double prime C, which is K prime C is 3.92 times K double prime C is 3.3 times 10 to the power of 4. 3.3 times 10 to the power of 4. This is the overall equilibrium constant for this overall reaction. Le Chatelier's principle. Le Chatelier's principle states that when a system at equilibrium is disturbed, then the system will shift its equilibrium position so as to counteract the effect of the disturbance. Now, what are the disturbances according to Le Chatelier principle? The disturbances are this: change in concentration or pressure of reactants or products by the addition or removal. Take a general equilibrium reaction. This reaction AM plus B in equilibrium with C plus D. Adding or removing concentration of reactants or products disturb reactions at equilibrium. Therefore, one of disturbance is addition or removal of concentration of reactants or products. The other is increasing or decreasing pressure of the system. The other disturbance is heating or cooling the reaction mixture, increasing or decreasing temperature of the reaction. These are the disturbances. Therefore, when a reaction at equilibrium is disturbed, then the system will shift its equilibrium position so as to counteract the effect of this disturbance. Let us see the disturbances or the stresses one by one. Effect of change in concentration on equilibrium position. Take this reaction. This reaction is equilibrium reaction. What happened to the equilibrium position if concentration of a reactant or a product is increase or decrease? Here it says, if the concentration or pressure of a substance is increased by the addition of more reactants or products, one, the equilibrium position will shift in the direction that consumes the added substance. For example, M plus B in equilibrium with C plus D. If concentration of M is increased, then equilibrium will shift in the direction that consumes concentration of M. On the other hand, if concentration of M is decreased, then equilibrium will shift in the direction that replenish the removed reactant, the removed substance. The equilibrium position will shift away from the increased concentration. For example, for the reaction at equilibrium, sodium bicarbonate in equilibrium with sodium carbonate, water and carbon dioxide gas, delta H for this reaction is 128 kilojoule. The forward reaction is endothermic. Now, what happened to the equilibrium position if concentration of carbon dioxide or the product carbon dioxide is removed? As predicted by Le Chatelier's principle, the equilibrium shift to the product side to replenish the removed carbon dioxide. Therefore, equilibrium shift to product side or equilibrium shift to the right. Beam adding sodium bicarbonate. Now sodium bicarbonate is a solid. If extra sodium bicarbonate is added to this equilibrium mixture, concentration of this solid is constant. Therefore, the equilibrium position is unchanged. No effects on equilibrium position. No effect on equilibrium position. Because sodium bicarbonate is a solid, concentration of a solid is constant. Effect of changing pressure on equilibrium position. What happened to the equilibrium position if pressure of the system is increased? According to Le Chatelier's principle, if the pressure at equilibrium is increased, then the reaction will proceed in that direction where the pressure is reduced. Since the pressure depends upon the number of moles, because from the ideal gas equation, pressure times volume equal N times R times temperature, we have this: pressure equal N divided by V times R times temperature. You see, pressure and volume are inversely proportional. Pressure depends on number of moles. For example, in the formation of ammonia from its element nitrogen gas plus 3H2 gas to form 2NH3 gas, an increase in pressure, if pressure is increased, then equilibrium shift in the direction that reduce the pressure. Equilibrium shift in the side that have small number of moles of gases. You see, on this side we have 1 plus 3, 4 moles of gases. On this side we have 2 mole of gas, 2 mole of gas. Therefore, when a pressure of this system increase, equilibrium shift to the side which have small number of moles of gases to the product side. If pressure of this system, if pressure of this reaction decrease, then equilibrium shift to the side which have large number of moles of gases to the reactant side. See, an increase in pressure at equilibrium will favor the formation of products, the formation of ammonia. Effect of changing temperature on equilibrium position and equilibrium constants casing of the reaction. The temperature dependence of the equilibrium position and the value of the equilibrium constant is dependent on the sign of delta H of the reaction. For example, take this reaction, formation of ammonia from its elements nitrogen gas plus hydrogen gas, 3H2 gas to form ammonia, 2NH3 gas. Delta H for this reaction is minus 92.2 kilojoule. The forward reaction is exothermic. The reverse reaction is endothermic. Now, if temperature of this equilibrium reaction increase, then equilibrium will shift to the direction that reduce the temperature to the endothermic side. Formation of reactants is favored if temperature is increased. If temperature decrease, equilibrium shift to exothermic side. Here it says the equilibrium constant for an exothermic reaction will decrease as temperature increases. Why? Because the equilibrium constant for this reaction, Kc, for this reaction is concentration of ammonia, NH3 to the power 2 divided by concentration of nitrogen times concentration of hydrogen to the power 3. The equilibrium constant for an exothermic reaction will decrease as temperature increase. When temperature of this equilibrium reaction increase, equilibrium shift to endothermic side. Therefore, concentration of ammonia decrease. Kc and concentration of ammonia are directly proportional. So, Kc also decrease. You see? Equilibrium position will shift to the left as temperature increases. B. The equilibrium constant for an endothermic reaction. Take one of the endothermic reaction. N2, O4 is a gas in equilibrium with 2NO2 gas. 2NO2 gas. Delta H for this reaction, delta H of the reaction is plus 57.2 kilojoule. Now the forward reaction is endothermic, the reverse reaction is exothermic. Here it says the equilibrium constant for an endothermic reaction will increase as the temperature increase. When temperature of this system increase, equilibrium shift to the product side. Formation of nitrogen dioxide favored. Therefore, the value of Kc increase because Kc and concentration of NO2 are directly proportional. Equilibrium position will shift to the right as temperature increases. You can take this as an example. A plus 2B in equilibrium with C plus D. Delta H for this reaction is minus 215 kilojoule per mole. The forward reaction is exothermic. When temperature of this reaction increase, equilibrium shift to endothermic side. Formation of reactants are favored. You see, the position of equilibrium moves to the left if you increase the temperature. Decreasing the temperature favors the exothermic reaction. For exothermic reaction, when temperature decrease, equilibrium shift to exothermic direction, to the product direction. Therefore, formation of products are favored. The main effects of temperature on equilibrium is, however, in changing the value of the equilibrium constant. As we said, the value of equilibrium constants Kc depends on temperature. You see, if the forward reaction is favored, more products are produced and fewer reactants, K equilibrium will increase. If the reverse reaction is favored, fewer products and more reactants, K equilibrium will decrease. Effects of a catalyst on equilibrium position. What is the effects of adding a catalyst into equilibrium reaction? Note that catalysts are substances that increase rate of the reaction by lowering the activation energy. Catalysts have no effects on equilibrium position. They only speed up the rate of the reaction. Hence, adding a catalyst will not affect the position of an equilibrium. A catalyst speeds up both the forward and reverse reactions, so there is no uneven change in reaction rates. Generally, a catalyst will help a reaction to reach the point of equilibrium sooner, but it will not affect the equilibrium otherwise. Optimum conditions. Optimum condition, the condition that gives maximum yield of the products, are known as optimum conditions. These conditions are decided by the enthalpy of the reaction, or heat of the reaction, and stoichiometry of the reaction. Now, for exothermic reaction, take one of the exothermic reaction, formation of ammonia from its element by the Haber process, nitrogen gas, N2 gas plus 3H2 gas, H2 gas to form ammonia, 2NH3 gas. Delta H for this reaction is minus 92.2 kilojoules. You see? The forward reaction is exothermic. For exothermic reactions, the yield of products is increased. The yield of product is increased by performing the reaction at lower temperature. When temperature is lowered, when temperature is decreased, equilibrium shift to the product side. Formation of ammonia, formation of the product is favored. 2. For endothermic reaction, again take one of an endothermic reaction, N2O4 gas in equilibrium with 2NO2 gas, delta H for this reaction, delta H of the reaction equal plus 57.2 kilojoule. Here it says for endothermic reaction, the yield of product is increased by performing the reaction at higher temperature. When temperature of this system increase, equilibrium shift to endothermic side. More products are formed. Therefore, formation of product is favored when temperature increase for endothermic reaction. Number 3, when delta N is greater than 0, the decrease in pressure favors the formation of product. Again, you can take this as an example. You see, delta N, change in number of mole equal the summation of number of mole of product minus the summation of number of mole of reactants. You see, the summation of number of mole of products for this is 2 minus 1 is 1, which is greater than 0. Therefore, when delta N is greater than 0, the decrease in pressure, if you decrease pressure for this reaction at equilibrium, then equilibrium shift to the side with more number of moles. Formation of product is favored. 4, when delta N is less than 0, take this as an example. You see, delta N less than 0, 2 minus 4 is minus 2, which is less than 0. The increase in pressure, if you increase pressure of this equilibrium reaction, equilibrium shift to the side with less number of moles to the product side. Formation of ammonia is favored. 5, removing the product from the reaction vessel. If you remove ammonia, then equilibrium shift to the product side to replenish the removed product. Hence, removing the product from the reaction vessel shifts the equilibrium reaction in the forward reaction. Students, in our today's lesson, we discussed factors affecting the equilibrium position. These are concentration, temperature, pressure, and volume. Again, we discussed factors that affect the equilibrium constant. The equilibrium constant Kc depends on temperature at which the experiment is performed. The equilibrium constant Kc is also affected by the form of equation that describe the equilibrium. We learned Le Chatelier's principle. Le Chatelier principle states that when a system at equilibrium is disturbed, then the system will shift its equilibrium position so as to counteract the effect of the disturbance. According to Le Chatelier principle, the disturbances are increasing or decreasing concentration of reactants or products, heating or cooling reaction mixtures, increasing or decreasing pressure of the system. These are the stresses, the disturbances. We learned optimum conditions. Optimum conditions are conditions that determine amount of the product. This brings us to the end of our today's lesson. Until next time, goodbye.